button. Thank you. Every morning when we have class, somebody please just say that because sometimes I'll remember, sometimes I won't. But thank you for reminding me. Yeah, so I try to record everything. I edit the cussing out though.
Oh.
All right, so let's go back to we did this first example yesterday. Not yesterday, Monday. Is that right?
Yes.
How did we show? Okay, so all the question was to draw all possible resonance forms, right? So in order to do resonance, what did we talk about the other day? We said you got to have what, a donor and an acceptor, and they got to be next door to one another. Is that right? Did y'all watch that resonance patterns video that I sent?
Mm-hmm.
Did it help or did it not add anything to you?
It helped me.
Yeah, I think knowing that how to identify those patterns actually helps you to quickly know, okay, this is what I need to do, right? Because once you know the pattern and the electron flow, it never changes. Every pattern has the same electron flow, just like this allylic radical right here. If I were to draw that out just as a chain, right, it's gonna do the same thing every time. Same three arrows, it's gonna rearrange the same way. Right, never changes. Never changes, excuse me. All right, so let's look at the next example. This is just to warm us up for this problem we get ready to do. All right, what do you think? Where's the pattern?
Does everything move to the right?
Oh, no, I'll speak out at once now. We won't want that to happen. Go ahead. What is that true, Juanita?
Does all the arrows move to the right?
Well,
so the double bond will go to the sigma bond right there, and then the next pi bond will go to that sigma, and then
okay. I think you're on the right track. So, are you first? Is this the pattern that you're looking at?
Yes.
Okay.
I was looking at all three, but I guess.
But you can't touch the other one yet because if you notice over here, you got a alkene, but you don't have any electrons to give it, so you don't have any donors.
Okay.
So you can only touch this alkene right here. Can't touch the other one yet. But you're right. Everything is going to move in that direction. Yes. So let's see what happens. Would you do this? Because keep in mind, it's these three carbons right here. Here, here, and here. Those are the three carbons that are seeing each other. Right? That's the allylic system that has the radicals. So that's what we're working with. Yes or no?
Yes. Dr. Russell.
So take a moment.
Dr. Russell.
Yes, go ahead.
What makes an allylic site again?
Because it's the carbon right here is adjacent to a double bond.
Right.
If that radical was here, it couldn't do resonance with that double bond. Right? All right. Anybody got it drawn?
Yeah, so you would make a double bond to the right of the radical and then move the double bond into a lone pair on that vertex.
Right here?
Yes.
Yeah, it's not a lone pair now. It's
just a radical.
Yeah, it's just a single electron.
All right, you can do another one.
And I need to put that back, right? I can't do another one, right?
Yeah, you could. Yep.
Because I got the same pattern right here, don't I?
Mm-hmm.
So it would be the same exact flow of electrons. Never changes. Right? Ever in life will it change, because as long as those three orbitals can overlap and see each other, they're going to be able to share electrons. Let me put the double bond inside the ring for somebody to have a baby. Oh my gosh, you can't do that. All right. Oh, hold up. That's going to be blocked on the recording. Get out of here, man. Jeez. Sorry. All right. Let me see what's in the chat. Oh, okay, yeah. All right. Any questions about that one?
So then what makes this question or this example, it stops on the third one?
Yeah, it stops there because there's nothing else for that, nowhere else for that radical to go. Are you following that? Except for backwards.
Okay.
Right. So I can, of course, I can do this. And that'll take me back to here. Right.
Right.
And I can take, if I erase these arrows, I could put arrows in to show how you could go back from here to here. That's why anytime you do resonance, you have these double-sided arrows because all of those resonance forms are interchangeable. All right. Any questions?
And these are the two products that we that we got from this one.
Yeah. So when you say products, now I want you to keep in mind when you say a product, that's from a reaction.
Mm-hmm.
Right? Resonance is not a reaction. So these are resonance forms. You have to be careful with that. Right. So these are resonance forms. If you say something is a product, that means you did a reaction to it.
Right.
Make sense?
Mm-hmm.
All right. All right. I wish I could break y'all out. I can break y'all out, but I don't know if I can let you share a screen for this last one. I want to take a moment and let y'all work through that. How many times you think that can do resonance? Is it gonna be more than one?
I believe so, yes.
You see, the first pattern is right there, isn't it?
Excuse me, yes.
All right. I wonder if you can annotate. Let me see if I could change the security preferences. Yeah, you can annotate. Does anybody see the annotate button on their screen? If you're using a laptop.
You gotta go to view.
You gotta go to this. Yeah.
Just click view options and then annotate is right there.
Yeah. Does somebody want to write in the arrows for that first structure, first resonance form? Or the arrows that'll get us to the first resonance form?
I could.
Come on with me. Who was that, by the way?
Me, one of them.
Okay, come on with it. Your confidence is brimming today. That's good. Okay, come on. Not bad. I'm in 100%. Well, I'm in 99% agreement with you. The 1% where I disagree is that you need to use fish hooks, single-headed arrows.
Okay.
Anytime you use a two-headed arrow, that means you're moving 2 electrons. Right? When you use a single-headed arrow, that means you're moving 1 electron. And anytime you're working with radicals, you got to use single-headed arrows.
Okay.
But the pattern itself is correct, right?
Mm-hmm.
So your other resonance form is going to look like this, where the double bond is now here, and then the radical is here, and then you have the aromatic ring over here. Do you see that pattern again? Is that right?
Yes. But then.
Go ahead.
Oh, never mind. I see it.
That's another allylic radical, isn't it?
Mm-hmm.
Because it's got a carbon right here that's adjacent to a double bond. Right? So we can do resonance again. Anybody want to put the arrows in for that one?
I would, but I don't think I can. My computer won't allow it.
Oh, you can't use your mouse pad to do it to
Oh
try.
yeah, I use my mouse.
Wait, so where do you go?
You have to find and annotate.
It says, you know how when you click on the thing, it'll say you are viewing Albert Russell's screen, and then click view options on the top.
Okay. Oh, annotate.
Yeah,
Yes. With that, and it should let you.
Oh, look at that. Okay.
look at that.
I did not know you could do that.
The Lord works in mysterious ways.
Okay.
Okay, and you got a half arrow, which is good.
With that move.
You need then you're gonna take one electron from the pi bond. Yep,
Move prints. Sorry.
great. And then the other electron is gonna go where? Great. That's exactly right. So you went here, here, and then here like that. You following?
Mm-hmm.
All fish hooks, because we're only moving one electron. So the resonance form is going to look like this, where these two double bonds. I'm getting a little sloppy here. Hold up.
So do we keep doing resonance until
Yeah, till you run out of.
we run out of Lilith sites?
Mm-hmm.
Hmm.
And then the only place to go then is to go backwards, right? So you got that, and you got that. So that is the resonance form from the arrows that you just put in. Oh man, this is so sloppy. Come on, Russell.
Dr. Russell?
Mm-hmm.
Will we always move it 3 times?
You talking about with the radical? Absolutely.
Okay.
The allylic, the electron flow to rearrange and the allylic radical never changes. So once you learn the pattern, then you know what arrows to use and how to put them in. It never changes.
So would this third one be the last one, or could you
Mhm.
keep going?
Don't you see the pattern? You see the pattern again right here, right?
Yeah, because
Okay, I just wanted to make sure I was right. Okay.
Yeah, you can do it again. And then that radical is going to end up here. I'm not going to draw the other ones because I think y'all catching it. Y'all getting the hang of it. And then you'll have the same pattern down there. So you'll be able to do it you'll be able to do 2 more resonance forms.
Okay.
when do we know when to stop? Or is it
It's kind of you stop when you don't have any more structure to draw. There's a kind of a rule of thumb, like if you add up the number of donors and acceptors, then that'll give you roughly the number of resonance forms you can draw. So if we say that one electron is a donor and we got 1, 2, 3, 4 pi bonds as acceptors, so you're going to get at least 5 resonance forms,
okay?
and that includes the original, right?
Mm-hmm.
All right, so that's good. That's a good warm up. Y'all can finish the other ones. I think you'll be able to do it. We got 2 of them. If you start here, you should be able to draw the other 2 that are possible. Oh, if you annotate it, I need you to erase your arrows because I can't do it.
Oh yes. Hold on.
There should be a little eraser somewhere on that toolbar.
Yes. Yeah. I'm sorry.
There's also the clear button.
Oh, well, you could do that too.
That works.
That's even faster. Excuse me. All right. So let's go back up and do another example. And we're gonna go through the mechanism and all that good stuff. Yeah, let's do this one. And then I'm gonna leave you to do the other one on your own, and then we're gonna start talking about these alcohols. Is that all right?
Yes.
Yeah.
I think I've given you enough tools that you can work on your own on a couple of these things. All right. Juanita, I need you to erase your arrows, please.
Okay.
Thank you. All right. I'm gonna keep the words. I'm gonna keep all that. All right. So let's go back to here. when we first, what's the strategy again? Keep in mind, we're doing allylic bromination, so we're looking to add bromine at the allylic site. Is that right? That's the first thing. So now we know what reaction we're doing. What's the other strategy? The other tool in the toolbox for this reaction? What do you need to find? Where the allylic site is, right?
Yeah.
So in this case, the allylic site is going to be.
Oh, we're doing this one.
Yeah, we're doing that one. We already did the top one.
Right. Tripping.
So that's my allylic site. Is that right?
Yes, because it's adjacent.
Adjacent to the double bond. Do I have another allylic site?
The one up there at the top.
This one. What's the problem with it?
Oh, they're both this.
But they're both allylic now. But this is what I want you to think. What happens during allylic bromination that makes it
The
possible?
hydrogen's attacked.
You take a hydrogen away off of that allylic carbon. That's exactly right. Now, if you look at that top carbon, are there any hydrogens there that can be abstracted?
Yeah,
No.
I know.
Who said yeah? Let me see.
I say yes. I say yes.
Let me see. So
Say
you know,
no.
you know on my end, your screen lights up when you say something.
Oh, hello. Yes.
So you're saying there's a hydrogen here?
Wait, where? There? Oh, down there?
Right here.
Oh. Oh, wait.
Count the bonds. Carbon can only make 4 bonds, right? So there's no hydrogen.
Never mind.
Yeah, never mind.
Okay, no, we go ahead and keep learning.
I know, I'm joking. I'm not throwing shade. I promise.
I know.
This is good. We need this. All right, so that allylic site is not going to give you a product because there's no hydrogens there. I'm gonna write that down for y'all.
You must have a hydrogen.
You gotta have at least one hydrogen on the allylic site in order for
Okay.
you to be able to brominate it, right? Because one of the main steps is pulling that hydrogen off. After initiation, when you get to propagation, that's what happens.
Oh, so many rules.
Yeah, but once you get it, you got it. All right, so we only got one allylic site. Let me fix that, sorry. Right? What does that mean? What did we talk about Monday? How do you know how many products you're gonna get? You can estimate that, can't you?
Yeah.
By doing what?
2 times the amount of allylic sites you have.
Yes.
Yes.
So you got one allylic site, so you're gonna get at least 2 products because what? Somebody help me. Praise the Lord. Somebody got about to bring the answer down from heaven. Come on. Why are we going to get 2 products?
Because there's one viable allylic site.
One site, and then what happens at that? What's possible at that site?
The bromination will
Is
come.
it?
Come on, I heard you. Come on, it's on the tip of your tongue. Is it
the resonant?
Rearrangement.
Yes, it's resonance rearrangement. Yes. Praise the Lord. All right. So here, let's go through this mechanism real quick. Right? So that's my starting material right here. All right. So initiation doesn't change. The MBS, you're going to break the NBR bond with light homolytic cleavage, so you get a bromine radical. The propagation step is going to be different. Let me erase all this stuff. I don't have a clear button. I might, I just don't know where it is for this app. All right. So on propagation, this is my starting material. That's so ugly. All right, that's my star material. Is that right?
Yes.
And this is my allylic site. So it's going to be that plus BR And that's going to give me what? And how do I do that abstraction? Remember, in propagation, that's what we do what's called abstraction, which is what? Anybody?
Moving the H.
Mm-hmm. So I'm removing H dot, right?
Mm-hmm.
So I'm going to put an arrow here. I'm going to put an arrow here and then one back to carbon. Is that right? This never changes. It's always the same 3 arrows. If you break the CH bond homolytically, 1 electron's going to carbon, 1 is leaving with hydrogen. So I get what? HBr, is that right? That's always a byproduct of the propagation step. And then what does my radical look like?
You would have a radical where the
It'd be
H
right
was.
there, wouldn't it?
Mm-hmm.
Is that right? Anybody cannot see
Yeah.
that? Say something.
No, I see it.
All right. If you don't see it, please say something so we don't leave you behind.
Wait, did we so I see you put 2 hydrogens there. Those are already there. You just wrote them out.
Yeah, I drew them out so you can see me breaking that bond.
Mm-hmm.
But every vertex is understood to be a CH2. Anywhere 2 lines come together on a skeletal form is understood to be a CH2.
Wait, did we do initiation?
Mhm.
I guess.
I cheated because I had it drawn on here from the other day.
Oh, okay. I think I took a picture.
Yeah. And I can like for this example, once we finish working it, I can actually send you this document.
Okay.
I can because I think in this app, all I have is a little send button. I can email it to you. All right. So now so now we have that allylic radical from propagation. What now? What can I do with it?
Resonance.
I can do resonance.
Oh, you can.
Mm-hmm. Zoom in so I can make my arrows look decent. All right. Can I do this?
Yes.
Mm-hmm. Is this becoming easier?
Mm-hmm.
Yes.
Yes. Way better than the first time.
Good.
Yeah,
That's the
I was
goal.
like, I
That's
did
the
not know
goal.
what was going on.
At least you're being honest about it. All right. Is that right? That's my resonance form.
Yes.
Wait a minute.
Oh,
Right there, right?
Oh, yes. Okay.
So now that's propagation. So I'm ripped off H dot, and then the radical that I made ended up rearranging through resonance. Everybody in agreement with that? So that resonance part is going to happen in the resonance part is going to happen during propagation.
Dr. Russell?
Yep.
Hold on. I'm about to annotate real quick. So for this right here,
Mm-hmm.
the bond, I see. I mean, I see it, the arrow told to move here.
Mm-hmm.
Which arrow tells it to come up here where it is?
On that carbon?
Yeah, because I see. I mean, I see. You know where this bond moved right here, but you know.
It's this one right here. You see the one I highlighted in green?
Right.
Mm-hmm. I'm gonna show you why.
Because it's like I don't know, maybe because it's like I'm not seeing like another arrow.
No,
maybe.
I think it's because it's in skeletal form, and that's not, and it's not making sense to you. That's okay. We're gonna make it make sense. All right. So let me put the double bond in. You see how these carbons are over here? How they all connected?
These.
Mm-hmm. The ones I just drew. Yeah.
Mm-hmm.
So if I put a radical right here, keep in mind it's only these 3 carbons that are considered to be a part of that allylic system.
Okay.
You follow?
Mm-hmm.
So for the allylic radical, it's only those 3 carbons. So when I put the arrows in, this is how it breaks apart. So that one electron is going to come from the double bond, and one is coming from that radical. So that's going to make the double bond shift to here.
Mm-hmm.
You following?
Yes.
Now there's still one electron left in the pi bond that you're breaking, right? And so that electron is going to end up coming to this carbon.
Oh, okay.
Right. So if I drew that out again in Lewis form, double bond will be down here now, and then the radical will be up here. That's how they get shaped.
Okay.
It's only those 3 atoms.
Okay, just wanted to make sure. It was looking kind of weird.
Yeah.
Okay.
Well, I got the electron all the way at Calhoun's. I should have put
Right.
it closer. That's all right. You could have just said that. Just put it closer.
I mean, you're a teacher. But
I'm not infallible, though. I make mistakes. So.
Right.
Yeah.
Well, thank you.
Yeah. You got it now. All right. Is anybody writing that down before I erase it? Or should I just screenshot it?
Let me take a picture real quick.
Okay. Yeah, go ahead. I think I'm going to start doing that too. Taking screenshots and then just sending y'all a big file, putting a big file of pictures on it.
Okay, I just finished writing it down.
Okay, cool. I took a picture of it too, so if somebody email me later, hey, did you get a picture of that? Nope, I erased it. All right, so that's the propagation. What's next?
Termination.
It's the same 3 steps. Every radical mechanism goes through the same 3 steps. So initiation, propagation, and then termination. So what do I do in termination? Somebody help me.
So were you at the bromine?
Yeah, you want to finalize the reaction, right? You're terminating off your radicals. And so you're going to take every radical that you made in propagation and you're going to pair it up with a bromine.
So the results you got in propagation, those will be the 2 products, correct?
Yeah.
And termination is you just finalizing those 2 products you just found, or however many products you get.
So yes, the radicals that you make in propagation are the precursors to your products.
Okay.
You follow what I'm saying?
Mm-hmm.
Because you don't get the product until you actually brominate that allylic site, which is what happens in termination. But you're right. Your thinking is spot on. So I want to, come on, 6-member ring. So I want to do this, right? Boom. That's one of my products. Is that right?
Yeah. Yes.
And then the other one's going to come from that other radical that I made through resonance, which was here. Is that right?
Oh, okay. Yes. Yeah. The course using the 2 that we got from propagation.
You always use whatever radicals you make in propagation. That's what's going to end up terminating.
So then the BR is going to go
wherever that dot is.
Yeah.
Mm-hmm. So it's here. BR. Boom. All right. Let me throw in another aspect to this reaction. All right. Which one of those do you think is going to be formed fastest?
Form faster?
Mm-hmm. Let me write that question down. So which product? I'm abbreviating product now. SPDT. Which product is formed faster? What do you think?
The second one?
Second?
Or no, the first. Oh wait, the first one I think.
This one?
I would say
Yeah, the first one.
Okay, tell me why. You're right.
I think because like on the second one, the what is that? The CH2 group is like, yeah, it's blocking. It's like acting like the umbrella thing over the bromine.
Okay, you're right. So the two methyl groups up top are kind of make that site kind of harder to get to. Is that what you're saying?
Yeah.
I agree with that.
Yeah, that's what I was thinking too, Oriana.
Yeah. So the top product is faster because the carbon where bromine is attacking is more accessible.
Because like the second one, because the bromine's in the way.
Well, the methyl groups are in the way, and with bromine being such a big atom, right? That's going to be a little bit of steric hindrance occurring, so it's going to increase the energy of that product a little bit. I'm just going to put down here. I'm going to put this in layman's term. Well, no, I'm going to use the scientific term first. So you get steric hindrance for this one, which means it's going to be slower. Does that make sense?
Yes.
The bromine is like it's got a huge atomic radius. So it's the site that's less substituted or more accessible is going to be you're going to form that product much faster. So the reactive site on this one is much more accessible. That's the reasoning for the rate, why it's formed faster. Any questions about that?
No, I think I'm okay.
Yeah, so one of the characteristics of this reaction is that the least substituted site or the more accessible site it always reacts faster. I'm gonna write that down for you.
You said the least.
I'm gonna write it down and give you a chance to write it down.
Got notes everywhere.
So it happens faster at more accessible sites. I'm gonna say reactive sites. All right, you're following that? So I'll put in a little example down here too. So if you had like a radical that was like right here versus a radical that was here, this will be faster.
Mm-hmm.
So a secondary radical versus a tertiary radical, the secondary radical is going to be that's going to react a lot faster with bromine.
Gotcha.
To clarify, the first one is because that radical is too close to the methyl group.
Well, it's not necessarily that it's so close. It's just that the carbon is more hindered because of the methyl groups.
Okay.
Yeah, good question. Any other questions about that? Did everybody get this down?
That's our practice.
Yeah.
All right, cool. So let's jump in. I want to start talking about another reaction. And there's a handout for this, but I don't want to waste time pulling it up. So, I got it memorized though, so it's okay. So we're going to talk about synthesis of alkyl halides from alcohols. And I'm going to send you a video after class that'll reinforce this. All right. So you basically have three methods. You got three methods, right? Two methods are specific for primary and secondary alcohols. And then one method is specific for tertiary alcohols. We're going to do that one first because it's the easiest one to remember. So two methods are you can use for primary and secondary, and then one method you can use for tertiary. All right. Is everybody familiar with what that primary, secondary, and tertiary means before we go any further? If not, don't be afraid to say something.
Can you say what it is one more time? I kind of forget.
All right. Thank you for your honesty. All right. So a primary alcohol would be an alcohol that looks like this, right? You see the carbon that the alcohol is attached to?
Yes.
It only has a bond to one other carbon. Right. So we call that a primary. Secondary alcohol would be like this, right? Where the alcohol is attached is bonded to two carbons. Somebody, I mean to cut you off, by the way, whoever that was, get ready to say something. Go ahead.
It was just about to that. You just answered it, basically.
I must be a prophet. Maybe I.
Oh my gosh.
You could drop your offering in the chat box. Sow your seed. All right, and then a tertiary will be like this, right?
Okay.
Where the alcohol, where the carbon where the alcohol is attached, it's got three carbons.
Okay.
Excuse me.
All right, just like the name.
Yeah. So this would be tertiary. Right. It's the same when you're talking about primary, secondary, and tertiary carbons. It's the same concept, same idea.
Okay.
All right. So one of so let me talk about this real quick. When you converting converting alcohols into alkyl halides, one of the things about the conversion is that you have to always, this is a key for this reaction, right? You have to make, let me say must, not have to. You must make OH a better leaving group. Right, you got it. You have to make it a better leaving group. OH it's a terrible leaving group. All right. How many of you know what somebody tell me what a leaving group is and what type of reaction involves a leaving group? No, speak out at once now. Okay, here.
Nucleophilic?
Say again.
Nucleophilic?
Okay, you're right. That's part of it. But nucleophilic what?
Substitution,
elimination.
Who was that?
For what? What was
Isn't
the
it
substitution?
Isn't it what makes it
Yeah, substitution and elimination.
So leaving groups are really kind of you see those when you do substitution and elimination. That's exactly right.
Isn't it also if it's a good if it's more acidic, makes it a better leaving group?
That's true. It's not the leaving group itself, it's the conjugate acid of the leaving group.
Okay.
Yeah, I'm glad you said that. Let's talk about that. That's a great point. So what a leaving group is a atom or a group of atoms. And I'm kind of jumping the gun here because when we talk about substitution and elimination, we're going to talk about that. I know y'all did it in part 1, but we're going to do it again, but in a little more detail. So it's an atom, a group of atoms that gets displaced in a substitution or an elimination. right? So it gets displaced. For all of the reactions of alcohols that being converted into alkyl halides, they're all substitution reactions. Like all three of them are substitutions. All right. Any questions so far? That's a must. In order for you to get rid of the OH group, you have to make the OH group a better leaving group. By itself, the OH is horrible. It's a horrible leaving group.
That's to get rid of the OH?
Yeah, because you want to substitute it with a halogen.
Right.
So in order to do that, you got to make it a better leaving group. It's a bad leaving group. The pKa, the way you judge leaving groups, somebody already said that, but I'll go ahead and say it now, say it again. You look at the pKa of the conjugate acid. That's a good gauge, a good way to gauge what's a good leaving group and what's a bad leaving group. So the conjugate acid of OH will be water, right? Which has a pKa of about 16 or 17, something like that. That's not very acidic, right? The more acidic the conjugate acid is, the better the leaving group is. Right? Any questions about that?
Place a conjugate acid.
So here's the thing. So you have, let me just jog back a little bit, and then we're going to jump in and do one of these reactions. So if you have an acid, the acid is HA, right? We call that an acid. A Bronsted acid, because it's going to give up H plus. When you take away H plus, then you get A minus plus H plus, right? So this is the conjugate base. You remember that from part 1 when y'all did pKa?
Yeah.
Right. So then if I have a base, come on now, and I protonate it. So if this is the base, then this is the conjugate acid. So the conjugate acid is just whatever that base is plus H plus. So if you want to know what the conjugate acid of a leaving group looks like, you just add H to it. Right. So up here, if we say the leaving group is OH, then the conjugate acid is going to be HOH, right? Or in this case, that's water, H2O. Did that answer your question?
Yes.
All right. Any other questions? So again, the bottom line is OH is a poor leaving group. Anybody remember what factors dictate leaving group ability or stability? Anybody remember that from part 1 when you were doing pKa and conjugate acids and conjugate bases? It's like a mnemonic. I think if depending on, I didn't teach it using the ARIO. It was like atom, resonance, induction, and I even forgot what the O is in REO. Atom, resonance, induction, and orbitals. Or I think the way I taught it in part 1 is hybridization, induction, resonance, electronegativity, and size. So all of those factors kind of help determine the pKa. But I don't want to get into that. That's a different discussion. All right, so let's look at reaction. We got time. We got a few more minutes. So the first reaction we're going to look at for converting alcohols into alkyl halides is addition of HX. Right, this is specific to tertiary alcohols. There's a reason for that.
Wait, is this like one of the first steps?
This is the first reaction that we're going to look at. It's addition of HX. So if I take a
What's
tertiary,
HX?
hmm
I said, what's HX again?
it's an acid, right? X,
Oh, acid.
chlorine, bromine. Right? It's any type of acid. But in this case, we'll use these halogen acids, right? HCl, HBr, HI.
And this is for we're doing this for the tertiary.
Yes.
So it depends. Are the steps still the same for no matter which, like
no.
if it's primary, secondary?
No, that's what I'm saying. Let me go back. So remember up here I said that there's 3 methods, but one method is specific for tertiary alcohols, and the other 2 methods you can use primary or secondary alcohols. Yeah, that's why. So addition of HX is specific for tertiary.
Oh, okay.
Right. So if I take a tertiary alcohol plus let's just say we're using HBr. Right, the product looks like this. Right, so you have a substitution basically between the Br here and the OH here, right? But it's not a direct substitution because again, OH is not a good leaving group. We're okay so far? Do you see what happened?
Yes, sir.
Yes.
So now this is my alkyl halide, right? And I created that or synthesized that from an alcohol. Right, that's the umbrella we're working under right now, converting alcohols to alkyl halides. Right, we already talked about allylic bromination being a way to make alkyl halides, and now we're talking about taking alcohols and turning them into alkyl halides. All right, so let's see how this works. Let's see how it works. So one rule of thumb that you may or may not have learned in part 1 is anytime you have an OH group and you put it around a proton source, it's going to get protonated. Keep in mind that OH has 2 lone pairs around it. Right? So it's going to, that B is terrible. So it's actually going to attack HBr. That's the first step. And notice my arrow, right? It's a double-sided or double-headed arrow. It's not single-headed. Right? And it's coming from the lone pair on oxygen. And it's stopping at the hydrogen. All of that matters, right? Because if you don't show, if you have the arrow starting and stopping anywhere, then that's not correct. You always start it at the source of the electrons and you stop it at the what we call the sink, right? So it's always source to sink. Do y'all remember that from part 1? Did y'all learn that when y'all talked about acids and bases and nucleophiles and electrophiles?
Yes.
Okay, good. All right. So then once I attack H, I'm also going to break the HBr bond. Let me put some lone pairs on bromine so you'll be able to see that. It's got 3 lone pairs around it. So when I break the HBr bond, I'm going to end up with this.
Is this just another tetrary example?
It's an example of how we would convert a tertiary using HX, right? Because that's my method for tertiaries. So I'll get that plus what?
VR with all the little pairs.
And bromine is negative. Are y'all following that so far? So the first step is what we call a proton transfer. Do y'all remember that term from part 1?
Yeah.
So it's a proton transfer. And then what do you think happens next? You think BR is just going to attack that?
Is it?
I think the oxygen's gonna leave off.
Water. So that's exactly what we did, right? So this, I'm glad you said, was that you, Natalie?
Mm-hmm.
This is now a leaving group. It wasn't before, now it is. Remember we said all these reactions had the same goal in the first part of it, which is to make OH a better leaving group. So now it's a much better leaving group, right? Much better. If that's the leaving group, the conjugate acid would be what? If H2O is the leaving group, what's the conjugate acid look like?
H.
Come on.
H3O.
It would be H3O, right? Is that plus a H, right? And it will still be positive, right? The hydronium ion is something like negative 1.7 or negative 1.8 pKa. So it's a much better leaving group. All right. So there won't be any direct attack. So BR right, it doesn't attack directly. Can somebody tell me why I can't? Think about it. Think about where does it have to attack? It's got to attack the same carbon where OH is that right?
Yeah.
What if I'm trying to turn it into alkyl halide? Why won't it do it? Why can't it do it directly? What about all this big old? Yeah, I was almost said something would have got me in trouble. For all this big old stuff out here, so they can't attack directly. So that means that I also need to show in the next step, right? OH. I think you already said that, Natalie, that the OH is going to leave, right? Well, not the OH, but the water, the leaving group is going to leave. That's the next step. So that's going to give me an intermediate, which looks like this. It gives me a carbocation intermediate. Right, plus Br minus, right? So in the second step, that's the loss of leaving group. Is that okay? That's not CG, by the way. Right, so first step is proton transfer. And then the second step is the loss of leaving group, giving me a carbocation. Now do you see why this is specific for tertiary alcohols?
Okay. I think.
Why? What is it about that carbocation that's different from a secondary carbocation or even a primary?
Aren't tertiaries with like the positive charge more stable?
Yes. Tertiary carbocations, that's the most stable carbocation that you can make. That's exactly right. Right? And so if you're going to use this method, you need to use it on a substrate that's going to give you a stable intermediate. Right? So that's why tertiaries are better suited to this method. It'll work on a secondary, but it'll be really slow. And the same with a primary, it'll be super slow, right? Because when you get to the intermediate part, that's going to be a problem because you're going to have a really unstable intermediate. Do y'all remember the trend for carbocation stability?
No.
Right, so you have tertiary, which is the most stable, then secondary, then primary, and then methyl, which is the least stable. So tertiary carbocation is the best carbocation that you can form if you had to make one. Right, so you do proton transfer, you do loss of leaving group to get to your intermediate, and then what do you think the final step is? What are we
The
trying to
final
get?
step would be bromine attacking.
The intermediate.
Yeah.
So I want to do this, right?
Yeah.
But I want to attack that, and that's going to give me my product plus water. Right? So proton transfer, loss of leaving group, and then formation of the carbocation.
Mhm.
And then, I'm sorry, carbocation formation, and then attack of the bromine nucleophile. All right. Any questions about that? We are a little bit over time. I apologize for that. I'm gonna write that down here.
Dr. Russell, is this gonna be on the exam?
You mean the mechanism or the problem? Cause see, let me explain something about the mechanism, right? Let's say I gave you all the structures, could you put the arrows in?
And like do resonance?
No, not resonance. I'm talking about here. Like if I gave you all the structures and asked you to put the arrows in for the mechanism, you think you could do it?
Yes.
So it's not you. I'm not going to ask you to memorize the mechanism, but I may give you the first step and give you all the structures and say put the arrows in to show how you get from point A to point B. You understand what I'm saying? I'm not expecting you after one lecture or half a lecture to spit this back out to me, right? But the arrow stuff that's just building on what you learned in part one, because it's all just nucleophile, electrophile chemistry or acid-base chemistry.
Yes, sir.
Yeah. So I'm not going to ask you to give you a blank sheet of paper and say propose a mechanism. Not at this point, because this is our first time seeing it. But if I give you all the structures and ask you to put in the arrows to go from point A to point B, I think that's doable. Between today and Friday, I think we're going to have a good grasp of that. All right. Any other questions? Would anybody want a copy of this? Because I can export it, I think.
Please.
Yes, sir.
Yes, please.
Yes.
All right. Let me not erase anything, and I'll just export this whole document. Hold up. I gotta stop sharing first before I can do that. All right. Where is it? Make sure I open up the right one. I can export them both. Yeah, so let me do that. If you put your email addresses into the chat, that's why I know who to send it to. Or would you rather me just put the PDF on Blackboard?
Yeah, I would say it might be easier for you to put it on
Yeah,
Blackboard.
just the Blackboard.
All right, I'll do that. I'll do that while the video is uploading to YouTube.